Okay, we were solving this problem last week, and let's continue. Okay, so we have an adiabatic nozzle. Nozzle looks like this. We have inlet number 1, exit number 2, and we know the pressure and temperature and velocity at the inlet. So 300 kilopascal is P1, 200 degrees Celsius is T2, and the velocity at the inlet is 45 meters per second. And we also have the exit condition. We also have the inlet area of the nozzle is 110. So area at the inlet is 110 centimeters square, and 1 square meter is 10,000 centimeters square. So you can determine the cross-sectional area in square meter. And at the exit, we have pressure P1 and P2, 100 kilopascal, and the velocity V2 is 180 meter per second. So we want to determine the mass flow rate. We did last time, but let's do it one more time. So if you want to determine mass flow rate, m dot can be determined by two different ways. One is density times volumetric flow rate. The other one is density times cross-sectional area times average velocity. In this case, we know the cross-sectional area. So this one divided by 1,000, 0.011 square meter, and the velocity is 45 meter per second. So if you know the density, we can determine the mass flow rate. And how can we determine the density of air? If you have air, which is a pure gas, we can use the ideal gas equation of a state, which is PV is RT. By the way, here, this density is the inverse of specific volume. So we can say this equation can be written as P over density is RT. What is the pressure? 300. What is the gas constant? 0.287. Temperature 200. In Kelvin 473. So from here you can determine the density. This one goes up here to determine the mass flow rate. So if you do, you can find the mass flow rate from this m dot is 1.094 kilogram per second. So that's what we did last week. So today we are going to determine the exit temperature of the air. So if you want to determine the exit temperature, we need to have the governing equation in this problem. That is going to be the energy balance equation. So what is the energy balance equation for a nozzle system? If you don't remember, you can start with the general energy balance equation. The general energy balance equation for steady state open system. So open steady state system, it is going to be Q in plus W in minus Q out minus W. I'm sorry, that is the energy balance equation for a closed system. For an open system, Q dot in plus W dot in plus M dot at the inlet. Inlet is number 1. So it is M dot number 1 times this mass flow rate at the inlet has 3 energies: specific enthalpy, specific kinetic energy, and specific potential energy. It's going to be the same as energy transfer out of this control volume. First, heat transfer, and energy transfer by work. and mass transfer at the inlet number at the exit number 2, m dot number 2. This one has three forms of energy: specific enthalpy, specific kinetic energy, specific potential energy. From this, there is no, this is an adiabatic nozzle system, which means there is no heat transfer. We don't expect any energy transfer by work for a nozzle or diffuser. And we can neglect potential energy change. Since we only have one inlet and one exit, the mass flow rate m dot at number 1 should be the same as m dot number 2. So this one is the same as this one. So we can cross them out. So what we have, h1 plus velocity 1 square over 2 is going to be h2 velocity 2 square over 2. Since we have h in either side and the specific kinetic energy in either side, why don't we move this one, the specific kinetic energy, to the right-hand side and specific enthalpy to the left-hand side? We can do that. And then the equation becomes h1 minus h2 is velocity 2 square minus velocity 1 square divided by 2. So that is the energy balance equation. Then we know the inlet velocity 45, the exit velocity 180. So the question is, can we determine h1 minus h2? If you have pure system like this, air, how can we determine h1 minus h2? Just for your information, one more time, we already did. In chapter 3, we studied that U2 minus U1 is CV T2 minus T1. H2 minus H1 is CP T2 minus T1. And here we have H1 minus H2. That is going to be CP T1 minus T2. CP T1 minus T2 is velocity 2 square minus velocity 1 square divided by 2. Then we want to determine this exit temperature. And do we know inlet temperature? Yes, 200. Do we know inlet velocity? Yes. Do we know exit velocity? Yes. So if you know CP, you can determine T2, no problem. So let's find this CP. By the way, there's one thing that you need to be careful. Here is, what is the unit of this specific heat? Usually the unit of this specific heat here is going to be kilojoule per kilogram degree C. What is the unit of temperature? Degree C. So this degree C can be cancelled, no problem. What is the unit on the right hand side? We have a velocity square. Velocity square is meter square per second square. Oh wait, we studied dimensional homogeneity in chapter 1 and we learned m square, meter square per second square is the same as joule per kilogram. You may remember when we studied, the power generation potential and the mechanical energy per unit mass. And we learned that meter square per second square is the same as joule per kilogram. And let's look at the unit on the left-hand side. Joule per kilogram? No, it is kilojoule per kilogram. This is joule per kilogram. So you need to be careful. If you want to use kilojoule per kilogram, make sure that you divide by not 2, but 2000. Then it's going to be kilojoule. Okay? Many people make a mistake here in the unit conversion. Usually thermal energy, enthalpy, the unit is going to be kilojoule. kinetic energy, potential energy, unit is joule. Okay? Because when we talk about conversion between thermal energy and mechanical energy, the amount of mechanical energy is much less than the amount of thermal energy. That's why most units in thermal energy are kilojoule. Most units in mechanical energy are joule. Okay? All right. So I get that. Now let's just determine T2. So what is the inlet velocity? Oh, we know that 45 meter per second. What is the exit velocity? We know that 180 meter per second. So the right-hand side of this equation is no problem. There's no problem here. What is the inlet temperature? 200. Okay. So we want to determine T2. If you know CP, you get T2. Where do we get this CP? Table A20. Where is the CP? For air, there's a CP. So, oh, wait. We were expecting just one value, and there are so many values. Why is that? Because most thermodynamic properties are temperature dependent. So we need to evaluate a specific value at the right temperature. Then you can use that value. Then what is the temperature? At what temperature do you need to, to evaluate this specific heat? The inlet temperature? The exit temperature? No, the average temperature. Okay, sounds simple. So let's find average temperature and then get this CP. Now there is a problem. Can you determine the average temperature? No, because we only know the inlet temperature. Then we cannot determine CP because we do not know the exit temperature. Can we determine this exit temperature somewhere else? No, we have to use this equation to determine the exit temperature. So now you see the problem. The thing that you want to calculate is required to solve this problem to determine that one. Make sense? Kind of confused in my brain, but so in that case, what do? We just give up? No, we can solve it by iteration. That is called numerical solution. When we hear about numerical solution, that is what we do. Okay, so to determine this CP, we cannot just determine CP, so we need to guess this T2. So let's guess. First guess. First means there's a second, right? First guess. This is the the iteration method. I'm going to assume T2 is some value. Anything. Let's say room temperature. I'm going to assume the exit temperature is room temperature, 20 degrees Celsius. Then based on this assumption, let's solve it. Okay, we can do that. Then we assumed T2 is 20 and T1 is 200. Then can you determine the average temperature? Yes. 20 plus 200 divided by 2. What is the average temperature? T average is going to be 220, 110. In Kelvin, 110 plus 273, 383 Kelvin is the average temperature. So let's find specific heat at 383. Unfortunately, we don't have 383. So what we need to do is we need to do linear interpolation. Let's assume that we did that. Approximately 1.011. So specific heat value at 383 Kelvin is going to be 1.011 kilojoule per kilogram degree C. Okay, so I'm going to use this specific heat. Goes in this equation to determine T2. So let's do that. I don't have the answer, so I'm going to use this calculator on my phone. Starting from here. 180 square minus 45 square divided by 2000 15 divided by 1.011 15.02 minus 200. I get 180.98. So from this, we got T2 is 184.98 degrees Celsius. Okay, so that's how you determine the final temperature. Are you happy with that solution? You are not happy. Why is that? There's something bothers you. What is that? I assumed 20. What I got is 184. Does it make sense? No, not really. So that means our assumption was not right. Okay, the first guess was wrong. Then let's do a second guess. So first guess, unfortunately, I was wrong. Second guess. Now let's assume again. T2. Now here's the problem. I'm going to assume another, the completely random number, 6,000 degrees Celsius, or 2.3 million degrees Celsius, or 3 billion. No, this time, since we have a clue from the first iteration, the final answer may not be this one, but could be close to this one. So our second guess is going to be T2 is this number. So I'm going to say T2, the exit temperature is this one, approximately 185 degrees Celsius from here. Then let's solve it again. The average temperature. The inlet temperature is 200. The exit temperature is 185. So the average temperature is 192.5 plus 273 in Kelvin, 465.5. 465.5 Kelvin. Okay, so I'm going to evaluate CP at this temperature, 465.5. So what is it? 465.5 is going to be between these two numbers. So we need to do a linear interpolation again. Approximately 465 is going to be close to 1.023. So our assumption is that specific heat is 1.023 kilojoule per kilogram degree C. Then I'm going to solve this equation one more time. Okay, let's do that. 180 square minus 45 square divided by 2,000 and divided by 1.023 minus 200. I get 185.2. So T2 from the second iteration is 185.2 degrees Celsius. Now, are you happy with this number? Our guess is 185. Now I got 185.2. I guess, yeah, that they are close enough. Then you can say, okay, this is the final answer. That is iteration method. Okay? Any question about how to find this final temperature? So whenever you need to determine a value and the value is required in the energy balance equation to determine that value, then you use this iteration method. Then the last problem is going to be the exit area of the nozzle. How do we determine this exit area? We can use the same equation that we used in A, the mass flow rate. The mass flow rate m dot is density times velocity times cross-sectional area. At this time, it's going to be the exit. So exit number 2, velocity number 2, area number 2. And we already determined the mass flow rate. Over there, 1.094. 1.094 kilogram per second. What is the exit velocity? 180 meter per second. What is the exit area? I don't know. That's what we want to determine. So if you know the density, you get the exit area. Now, can we determine the density? Yes, the same equation that we did in the first question. We can use the ideal gas equation of a state. What is the ideal gas equation of a state? PV is RT. Wait, there's no density. Density is the inverse of this specific volume. So this can be rewritten as P over a density is RT. So what is the exit pressure? 100. So this one is 100 kilopascal. What is the gas constant? 0.287 kilojoule per kilogram Kelvin. What is the exit temperature? We just found 185.2 plus 273. So can you determine the density? Yes. We can determine the density. That goes into this mass balance equation. Then you can find the cross-sectional area, which is 79.9 centimeters square. That's how you solve this problem. Any question? Is it too fast, too slow? Too fast, okay. Now, we are going to talk about another thermodynamic device, this time turbines and compressors. What is turbine? Turbine is a device to convert thermal energy into mechanical energy. Then why do we study turbines and compressors at the same time? Because they are close to each other. Turbines are devices that convert thermal energy into mechanical energy. On the other hand, compressor is a device to convert mechanical energy into thermal energy. So they do the opposite things. So this one create mechanical energy from thermal energy. This one create thermal energy from mechanical energy. Then you may want to know, okay, I get that. One is converting, the thermal energy into mechanical energy. The other is converting mechanical energy into thermal energy. But how? Yes, how is the most important thing, right? So let's talk about the physics of these turbines and compressors. By the way, where do we use turbines? Do we see them in our real life? Not really. Do we use them in our real life? Yes, a lot. How do we produce electricity? Turbine. More than 90% of the electricity that we produce are from turbine. What about compressor? Do we use compressor every day? Yes. Is there a compressor in this room? Yes. Where is it? Air conditioning system. What about in your house? Refrigeration system. What about in your car? There's also refrigeration system. What about in winter? The heat pump systems that heat your house. So turbines and compressors are used in many, many places in our real life. Then you may want to know how they work. It's actually very simple. So let's talk about turbine first, because they are similar to each other. So I'm going to talk about turbine and compressors at the same time. So let's talk about turbine first. Turbine looks like this. Oh, we have an inlet. It's an open system. When you have an inlet, what do you have? Exit. So this one looks like a turbine. There's a turbine blade inside, like a fan. So what turbine does? It converts thermal energy into mechanical energy. So what determines thermal energy? When we say this water has high thermal energy, when water is on ice, not really. When water is a steam, maybe. So when water has high thermal energy, that means you heat that water. When you heat that water, then its thermal energy goes up, right? So what happens if you heat water? Becomes ice? No, the other way, it becomes steam. So when you heat water, in other words, when the thermal energy of water goes up, that means that you have water in the form of steam. That means temperature is high, pressure is high. So high pressure, high temperature steam enters this turbine. So there's a high pressure, high temperature steam enters this turbine. So that's the inlet. What happens? It is under high pressure, under high temperature. What happens if you just leave it? This is high temperature, high, the pressure. Steam. It compresses more? No. It will try to expand because it is under high pressure. It wants to expand. So how can it expand? This way? Look at the shape of this device. It's going to expand this way. Then what is blocking that expansion? Fan. So if it expands, when it expands, it pushes these fans. So when you push these fans, what happens to this, the fan and shaft? They rotate. So while they are expanding through the turbine, it rotates this shaft. So produce what? Shaft power. So this one produces shaft power. W dot out. Okay, so because of the expansion of this high temperature steam and high pressure steam, we create this shaft power. So what do we do with it? We couple this shaft with a generator. Then it produces electricity. That's what we do in many of the power plants over there. That's what we use, this electricity. Then what happens after this expansion? Oh, there used to be new high pressure, high temperature steam continuously enters this turbine. So whatever happens inside need to be removed through exit. So at this exit, do we still have high pressure, high temperature steam? Not anymore, because they already expanded. When they expand, temperature goes down, the pressure goes down. So at the end, we have low temperature, low pressure steam exits this turbine. So initially, the steam has large thermal energy, and that large thermal energy is converted to mechanical energy, which is this shaft power. And then left over with the water without power is going to be removed. Your job is done, go away, like that. So that's how thermal energy of the water is going to be converted to mechanical energy, shaft power. That's how turbine works. Okay, very simple to understand. Then what about compressor? So since we are studying turbine compressor at the same time, the compressor should look like this one. Okay, yeah, you're right. But slightly different. Oh, I forgot to add inlet here. So there's an inlet, there's an exit. Now the same thing, we have a shaft. Going to what? Rotate. Yes, you're right. And we have a turbine and a compressor. There's a blade inside. What happens? In compressor, it does the opposite thing of this turbine. Thermal energy becomes mechanical energy. In here, mechanical energy becomes thermal energy. So in compressor, mechanical energy is converted to thermal energy. What is mechanical energy in this turbine? This one, the rotation of the shaft. So if we provide shaft power, W dot, not out, in. So if we rotate this shaft, what happens? There's a low temperature, low pressure gas enters this compressor, and this shaft is rotating, pushing this, the working gas to the right-hand side. And due to the shape of this compressor, what happens? That pressurize the working gas. So its temperature goes up, its pressure goes up at the exit. So at the exit, we have high temperature, high pressure gas exits this compressor. So we provide mechanical energy, mechanical work to increase the temperature and pressure of the working gas. When temperature of the pressure of the working gas goes up, what does it mean? Its thermal energy goes up. So in this case, high pressure, the high temperature steam create shaft power. In this case, shaft power is given to pressurize the system. So now it makes sense to study turbine compressor at the same time because they work similar. And one is going this way, the other way is going this way. So in one way, we convert thermal energy into mechanical energy. In the other way, we convert mechanical energy into thermal energy. So that is the physics for the turbine and for the compressor. So now everybody understands that what turbine does and what compressor does, right? Now, what is the next step? Now we know how they work. We need to use mathematics. We need to study the mathematics of this turbine and compressor. What kind of mathematics? Governing equations. What kind of governing equations that we studied in the previous slide? Mass balance equation and energy balance equation. So we will do the same. Mass balance and energy balance. What is mass balance? mass transfer goes in. But by the way, let's say inlet is number one, inlet is number one, exit is number two, exit is number two. So according to the mass balance, m dot at the inlet should be the same as m dot at the exit. Do we have to say m dot number one, m dot number two? They are the same. So we can just say m dot. There's no difference between m dot at the inlet, m dot at the exit. They are the same. What about here? Mass balance. The same thing. M dot at the inlet should be the same as m dot at the exit. So just m dot is okay. So that's the mass balance for turbine and compressor. Are they difficult? Not at all, right? That's pretty easy to understand. Since mass cannot be destroyed or created, since we only have one inlet, one exit, the mass flow rate should remain constant. Okay, no problem. Now, let's talk about energy balance. Oh, energy balance should be more complicated than mass balance, so should be difficult. Not at all. Start with the general energy balance equation all the time, okay? And you can use, your understanding of the physics to simplify that energy balance equation. So what is the energy balance equation? For open, steady state, we use the same energy balance equation all the time. Q dot in plus W dot in plus energy transfer at the inlet. M dot at the inlet, this one has three forms of energy. One is enthalpy, the other one is kinetic energy, the last one is potential energy. It's going to be Q dot out plus W dot out plus M dot at the exit. Exit is number two. This one has enthalpy, kinetic energy, and potential energy. So that is the energy balance equation that we are going to use for this turbine. Oh, what about this compressor? Oh, I'm going to write again. So let's repeat the same energy balance equation. Q dot in, W dot in plus M dot at the inlet. This one has enthalpy, kinetic energy, and potential energy. It's going to be Q dot out plus W dot out plus M dot at the exit. This one has specific enthalpy, kinetic energy, and potential energy. Okay, this was the hardest part because the general energy balance equation is not short, pretty long, right? Okay, now let's evaluate each term one by one. So when we run a turbine, what is the first one? Do we heat a turbine? No. Why do we heat turbine? You want to, consume more energy? No, we neglect Q dot in. What about compressor? When you run your refrigerator, you heat the refrigerator to work better? No, it doesn't make sense. There's no Q dot in. This turbine produces W out. Then is there W in? No, so you can neglect W in. What about in compressor? Is there W in? Yes, that is the mechanical energy input. So we have W dot in. What about at the inlet? Oh, this one has a temperature and pressure. It means it has thermal energy. It means it has enthalpy, right? So there's an enthalpy. Is there kinetic energy? Maybe. Is there potential energy? Maybe. Then what is the difference between the kinetic energy at the inlet and the kinetic energy at the exit? Not much difference. What about potential energy at the inlet and the potential energy at the exit? Unless this turbine is taller than Mountain Everest, we neglect potential energy change between the inlet and the exit. Oh, this is Mountain Everest. So you can neglect kinetic energy change, potential energy change. Same goes to this compressor. We neglect kinetic energy change and potential energy change. Now, heat loss. Oh, it's case by case. Sometimes you have a very well insulated turbine, then you can neglect heat loss. But sometimes the insulation may not be that great. So this heat loss, Q dot out, is case by case. So triangle, case by case. What about W dot out? Yeah, there is W dot out. Turbine produces shaft power. So we have this term. What about compressor? Compressor, the produces work? No, it consumes the work. So there's no W dot out. What about, the exit? Oh, the mass leaving, the working gas leaving the exit has temperature and pressure. That means it has enthalpy. That means it has enthalpy. How many inlet? How many exit? Just one. So m dot number one is the same as m dot number two, just m dot. M dot number one is the same as m dot number two, just m dot. So I can remove subscript. Then the energy balance equation for turbine is going to be m dot h1 plus is q dot out. This is case by case. Plus w dot out plus m dot h2. That is the energy balance equation for this turbine. What about compressor? W dot in plus m dot h1 is q dot out. This is again case by case plus m dot h2. That is the energy balance equation for the compressor. That's everything about the physics and the mathematics of turbine and compressor. Any question? We never know when if we have a question or not, unless we actually solve a problem, right? So let's solve a problem together. We have a refrigerant 134A enters a compressor. Oh, now we have a compressor. What is the energy balance equation? We can use this one. So we have a compressor. Okay, the energy balance equation is this one. W dot in plus m dot h1 is q dot out plus m dot h2. Okay, that is, so we already know the governing equation. And we have R134A. We have the exit inlet condition. P1 is 180 kilopascal, and it is a saturated vapor phase change process number 4. That's great, because if you know it is saturated vapor, finding HVU should be super easy, right? Like a piece of cake. I actually don't understand piece of cake. It's not easy to eat a piece of cake, especially when you're full, when it's super greasy. Eating piece of cake is not easy. Anyway, it's a piece of cake, right? Super difficult. So, and the flow rate is 0.35 cubic meters per minute. So that is 31 dot volumetric flow rate, 0.35 cubic meters per minute. What is V dot, volumetric flow rate? What do we do with it? We can calculate the mass flow rate, because m dot is density times volumetric flow rate. Some people kind of, frustrated when they see this unusual unit. But you need to think differently. When you see this kind of unusual unit, cubic meters, not second per minute, why people, to develop a problem like that? Because the main problem is super easy. So trying to, to twist the problem a little bit. So whenever you see those stupid units, you should be happy. Okay, the main problem is going to be super easy. Isn't it? Let's see if that's the case. Okay, and the exit condition, 700 kilopascal. Okay, so we have exit. P2 is 700 kilopascal. That's it? Yeah, that's it. Then we know there's a problem here. Here we have a saturated vapor. So if you know pressure, you can find anything. You can find specific volume. V is Vg. If you want H, H is Hg, so no problem. But here, oh, you only have pressure. You need to know at least two information, but only one. That means that you need to determine something else here by using this energy balance equation. Then what is that? Let's see. So we need to determine something. And the power supplied to the refrigerant, W dot in, is 2.35. Okay, so this one is 2.35 kilowatt. What is the temperature at the exit? Oh, we need to determine the temperature at the exit. Now we get the idea. So using this equation, we know we can determine H1, and m dot can be found from this volumetric flow rate, and there is no information about heat loss. So we can assume that this is an adiabatic compressor, neglecting Q dot out. Since we can find m dot from here, we can find H1 from here, then you can determine H2. Once you know H2, P2, you can find T2. That's the plan. So which one first? M dot. So if you want to determine m dot, we need to know specific density. Oh, in thermodynamics, we don't use density. We use specific volume. The density, the inverse of specific volume. So this one is V dot divided by specific volume. So if you know specific volume, you can find the mass flow rate. So let's determine the specific volume. How can we do that? Oh wait, it's a saturated vapor. If you have a saturated vapor, V1 is just Vg. But not just Vg. This is the Vg at the given condition. What is the condition? 180. Vg at 180 kilopascal. So where can we find Vg at 180 kilopascal? From this pressure. So we go to the pressure table. There is a pressure table, 180 kilopascal. Where is Vg? This one, 0.1098. This one at 180 kilopascal, Vg, 0.1098 cubic meters per kilogram. Then let's use this equation. M dot should be V dot over V, and in that case, V dot is 0.35 cubic meters per minute. Oh no. So 1 minute is 50 seconds. No, 60 seconds. Divided by specific volume, this one, 0.1098 cubic meters per kilogram. Then we have minute, cubic meter. So we have a kilogram per second. So what is the mass flow rate? Do I have it? 0.0531. 0.0531 kilogram per second. That's how we determine the mass flow rate. Then going back to this energy balance equation, now we know m dot 0.0531. 0.0531. So now H1, how can we determine H1? Again, this is saturated vapor, so H1 is Hg. At what condition? At 180. At 180 kilopascal. Where can you find it? From this pressure. From this pressure. Where is Hg? Here is Hg. At this pressure. The value we are looking for is 239.71. This one. 239.71 kilojoule per kilogram. So now we put this number back to this equation, 239.71 kilojoule per kilogram. Now we have everything but H2. Can you determine H2 from this energy balance equation? Yes, you can. So from this, we can determine H2. That H2 is 283.97 kilojoule per kilogram. Now we have pressure and H2, 700 kilopascal. So if you know pressure and H, can you determine T? Yes, we can. A simple table problem that you saw in the first exam. So how can you solve it? T is 700 kilopascal. And then we can make T H diagram. This TH diagram looks like this. That's T set. That's HF. That's HG. So let's find T set HF HG. From where? From 700. From 700. Don't have it, but don't worry about that. I have a property table at 700. At 700, T set is this one, 26.72 degrees Celsius. HF is 86.78. HG is 261.85. And on this pH diagram, we know there is compressed liquid number 1, saturated liquid number 2, saturated mixture number 3, saturated vapor number 4, superheated vapor number 5. So we made this TH diagram using this pressure. Now, we need to find this H on this TH diagram. So what is our H? 287.3. H is this horizontal axis. 283 is greater than 86, greater than 261. So 283 should be on the right-hand side here. So what is the phase change process? Number 7? No, number 5, superheat vapor. So when you know it is phase change process number 5, then you go to superheat vapor table. Here is the superheat vapor table. 700 kilopascal. What is H? 283. This is V, this is U, this is H. So H is 283. Greater than this one, less than this one, between these two numbers. Between these two numbers. So what is the temperature between these two numbers? So what can you do? Linear interpolation between these two numbers for this value, then you can find temperature between 40 and 50. Since you know how to do a linear interpolation, I'm not going to do that. E2 is going to be 47.71 degrees Celsius. If you're not 100% sure about linear interpolation, so the left-hand side is temperature, T. The right-hand side is H. The lower bound of the temperature is 40. The upper bound is 50. So 40, 50. The corresponding H values are this one and this one. 275.93 to 86.35. Now, what is the H value that we have? 283.97. What is the location of this one? What is the position of this one? Top left on the right. Top left on the left is going to be the unknown temperature T. And this 50 goes up here. This 286.35 goes up here. If you find this T, that is 47.71. That's how you do linear interpolation. Any question? Every time you practice, you solve a problem, you need to ask yourself, if I see this problem in my second exam, can I solve it? If you can, no worry. If you cannot, then go look at the, the lecture video and then follow, what I did again. And if you're not 100% sure, then go to the homework assignment and solve the homework assignment problems until you 100%. Okay, solving this problem. And if you have no difficulty solving any of the problems in the PowerPoint and the homework assignment, you will get 100 out of 100 in the second exam. That's thermodynamics. There's no surprise. So are we okay? Go to the next, the device? Maybe not. Oh, we studied turbine and compressor. We only see a compressor. I want to see a turbine, but this problem is super easy. Okay, I understand that. So there is a turbine problem, which is a little bit more challenging than the previous problem. I knew that you are not very happy with the previous problem. That was super easy. So let's find something challenging. So this is the one. So if you can solve this one, no problem solving the previous one, right? I have 13 minutes. That's plenty of time. So let's talk about, this time it's a turbine. Okay, so how this turbine works. Turbine looks like this. We have one inlet, number one, and there's a shaft, and etc. We produce W dot out, and we have an exit. So let's see. Steady flow turbine, the mass flow rate is given. Okay, I don't have to calculate mass flow rate. How nice it is. M dot number one is 20 kilogram per second. Oh, we know pressure and temperature. Wow, that's very kind, right? So P1 is 4 megapascal and T1 is 600 degrees Celsius. So there is no problem in the inlet, right? So we know pressure, temperature, we even know the mass flow rate. Now, the steam expands in the turbine to a saturated vapor at 500. Wow, we know it is saturated vapor and it is 500. We know everything, so very good. But there's a problem where 10% of the steam is removed. So the flow rate, mass flow rate at the exit number 2 is only 10% of 20 kilogram per second. Then what happened to the 90%? Oh, there is another exit for 90%. Now you can see this one is slightly more challenging than the previous problem. Then what is the mass flow rate at number 2? Only 10% of 20. So m dot number 2 is only 10%, 2 kilogram per second. But we know pressure, P2 is 500 kilopascal, and we know it is a phase change process number 4, saturated vapor. And the remainder of the steam continues to expand to the turbine exit number 3. And the pressure is 10. By the way, mass flow rate is going to be 20 minus 2, 18 kilogram per second. P3 is 10 kilopascal. The quality X, if you have quality X, that means it is a saturated mixture. Now, we want to determine W dot out, the rate of work done, W dot out. Okay, we can do that. So what do we do first? We understand the physics now. We have 1 inlet, 2 exit. Now we need to talk about mathematics. What is the mathematics in this thermodynamics? Energy balance equation. Then what is the energy balance equation? Oh, we cannot use the energy balance equation, this simple energy balance equation anymore, because now we have 2 exits. So whenever you have this interesting device, always start with the general energy balance equation. What is the general energy balance equation? Q dot in plus W dot in. Now we have a mass transfer, mass flow rate at the inlet. M dot at the inlet. And this mass flow rate has what? 3 forms of energy. Enthalpy, kinetic energy, and potential energy. And those 3 are energy transfers into the system. Now there are 3 energy transfers out of the system. First, heat. And second, work. And last, energy by mass. Energy, m dot at the that goes out of the system. And what kind of energy going out of the system? There are 3 forms of energy. Enthalpy, kinetic energy, and potential energy. Okay, so that's the general energy balance equation. Now what do we do? We evaluate one by one based on the physics that we know. First of all, there is no information about heat transfer. Then you can assume that this one is an adiabatic turbine. It's a good insulation, so you neglect heat transfer. And it's a turbine that produces power. It does not consume power, so there's no W dot in. We usually neglect kinetic energy change and potential energy change. So what do we have? The rate of enthalpy at the inlet, W dot out, the rate of enthalpy at the exit. So what is the rate of enthalpy at the inlet? Inlet is number 1. So m dot number 1, H1. Okay, no problem. Then we have W dot out, the unknown that we want to calculate, and the rate of enthalpy at the exit. What is the rate of enthalpy at the exit? Not just 1, we have 2 and 3. Okay, m dot 2 and its enthalpy, m dot 3 and its enthalpy. So this is the energy balance equation. Do we know m dot? Yes, 2218. 2218. We want to determine this w dot out. So if you know H1, H2, H3, you can find w dot out. Now, is it hard? Not anymore. Once you write the energy balance equation, once you evaluate each term, now the rest of them is going to be the table problem in the first exam. So let's do that. 4 megapascal, 600 degrees Celsius. What is the phase change process? We know it's going to be superheat vapor, but let's verify that. How can we do that? At this pressure, 4 megapascal, we can make TH diagram. TH diagram looks like this. To complete this TH diagram, we need to know T set, HF, HG. Where can you find T set, HF, HG? From 4 megapascal. At 4 megapascal, T set is 250.4. So this one is 250.4. HF is this one, 1087 something. HG, 2801 point something. Now, on this TH diagram, 1, 2, 3, 4, 6, no 5. That is the TH diagram at 4 megapascal. Then, do we know any other property at the inlet? Yes, temperature, 600. So let's find 600. On this TH, T set is on this 250. Where is 600? Up here. So what is the phase change process? Number 6? No, number 5. Superheat vapor. So if you know superheat vapor, how can you find this H from superheat vapor table? So superheat vapor table is table A4. So the number you're looking for is somewhere down here. I don't have it, but don't worry about that. I have this table A4, and let's find 4 megapascal at 600 degrees Celsius. H1 is 3674.4. 3674.4. Okay. That was easy, right? What about H2? Oh, at number 2, we have a saturated vapor. If you have saturated vapor, how do you determine H? Hg. At what condition? This condition, 500. Hg at 500. So how can we find Hg at 500? At 500 kilopascal, Hg is this one, 2748.7. 2748.7. Okay, no problem. The last one, 83. What is the phase change process at number 3? Oh, we have quality X between 0 and 1. That means we have mixture. If you have a mixture, how do you determine its enthalpy? By using linear interpolation. That is HF plus quality X times Hg minus HF. From here, what is HF? At 10 kilopascal, HF 191.83. Hg at 10 kilopascal, this one 2584.7. What is the quality X? 0.85. So can you find H3? Yes, you can. H3 is going to be 2225.8. Now we have everything. Can you determine W dot out? Yes, you can. W dot out is going to be 2796.2 kilowatt. Any question? So that completes turbines and compressors. That's all for today. And this Thursday, we are going to talk about throttling valves, mixing chambers, and heat exchangers. That will be all for chapter 4. And you can expect a new homework due a week from this Thursday. So that's going to be next Thursday for chapter 4. So that's the plan. Okay. Thank you. See you not next week, this Thursday.